I am going to basically let the speakers introduce themselves, and we'll have some time for questions afterwards. So the first speaker is Dr. Ken Calderia, and I'm going to let him introduce himself. Thank you.
Hi, so I work at the Carnegie Institution Department of Global Ecology, which is really part of Carnegie Institution, but it's located on the Stanford campus. And so, this is on. So, and I research a whole range of things having to do with climate change and ocean acidification. And tonight this program is about non-traditional ways of addressing this climate, carbon, energy problem. And the general rubric is the word geoengineering. I just want to start off by putting that in a broader context. And you can think of this whole problem as now I forget how. Okay, that so we have a desire for improved well-being, which drives us to want to consume more and more goods and services, which leads to increasing demand for energy, which is leading to increased CO2 emissions, which leads to more CO2 in the atmosphere, which is causing climate change and ocean acidification, and that can impact on humans and ecosystems and ultimately subvert our effort to improve our well-being. And so I think we've come to the point where we need to think about each of these different arrows as potential intervention points that we can try to break this vicious circle. And so the conservation, we try to achieve our well-being without so much consumption. Efficiency, this is coming off the board here. Efficiency, we try to meet our demand for goods and services with less energy. Low carbon energy sources or carbon neutral energy sources such as solar, photovoltaics, or maybe nuclear tries to provide the CO2 emissions, to provide that demand for energy without the CO2 emissions. And then there's this concept known as carbon dioxide removal, which I'll go into in a bit, but the thing you're probably most familiar with is the idea of planting trees to take carbon dioxide out of the atmosphere and try to break the link between these emissions and atmospheric CO2 increases. And then what's here called climate engineering or solar radiation management tries to break this link between CO2 in the atmosphere and climate change. And then adaptation, sorry this is rolling off the screen, adaptation is the name for trying to change human systems or perhaps even natural systems so they're less vulnerable to the climate change that does occur. And so I think nobody who will be speaking tonight is presenting what they're presenting as the end-all and be-all of how to deal with the carbon climate problem, but to say that there's a whole range of approaches, and we just need to be careful not to bring anything off the table prematurely. So one of the things that got me involved in this whole area is just looking at curves like this, where this is a range of scenarios from the Intergovernmental Panel on Climate Change and predictions of amounts of climate change. And if you notice that all of these, even the most optimistic scenario, temperatures continue to increase throughout this century. And so right now we're evolving along the upper end of this trajectory. And if we work really hard to reduce emissions, we'll get towards the lower end of this trajectory. But there's really no practical way for emissions reduction, this greenhouse gas emissions, to actually reduce temperatures this century. It can slow rates and amounts of warming, but it can't actually turn things over. And so, if there is some sort of climate emergency somewhere in here, that, let's say there's massive famines and crop failures around the world, that the prospect is for things to continue getting worse after that occurs, not to get better, because it takes many decades to feel the full force of the greenhouse gas emission, and it takes many decades to change the course of our energy system, our energy infrastructure. So if we look in 1991, in June, there was a huge volcano known as Mount Pinatubo, and the next year, the Earth cooled around half a degree Celsius, which is about 1 degree Fahrenheit. And had that material stayed, so the material is fell out of the stratosphere within about a year or so. But had that material stayed in the stratosphere, it would have been enough to offset all of the global warming anticipated this century. And the amount of material is such that, that if you had a single fire hose constantly emitting dust particles into the stratosphere, that's one fire hose would have been enough to produce that entire cooling. It's okay if you feel. Okay, so the name geoengineering was in the title of this talk. There's basically, everybody has their own conception of what's included as geoengineering or what's not included. And so there's not a commonly accepted definition, but typical elements that appear in people's definitions are that it's intentional. So that our adding CO2 to the atmosphere, we know that's changing climate, but we're not, when we drive our cars, we're not intending to change climate. It's large scale, so most people want to call planting single tree geoengineering. And it involves alteration of natural systems. Also, it's novel or unfamiliar, that usually things that people are already kind of accepted, they don't want to call geoengineering. So planting forests, a lot of people don't want to call geoengineering. And the goal is usually to diminish climate change impacts or the amounts of climate change. So just to have a little cartoon of Earth's energy balance here, I'm trying to remember how to do this thing here. So the Earth's heated by the sunlight coming in, and then some of that sunlight bounces back out, and the sunlight then that heats the Earth's surface, and then the Earth loses that energy back out to space by radiating it upward as heat radiation or long-wave radiation. Greenhouse gases in the atmosphere absorb that radiation and send some of it back down and some of it back up. And so if you don't have greenhouse gases, the Earth would be much colder. As greenhouse gases accumulate, the Earth gets warmer. And so you could think of there's two basic strategies for keeping the planet from warming up. It's don't put so many greenhouse gases in the atmosphere or take them out of the atmosphere. Or you could also reduce the amount of heating force from the sun. And so the two broad options that I'll talk about here, one's called carbon dioxide removal options, and the other is what's called solar radiation management options, or sunlight reflection methods, or there's all different names. So these are very different in that those carbon dioxide removal options tend to be slow. They tend to either be expensive or not scalable, so there's some things that might be cost effective and deal with some percentage of the overall problem, but not scalable enough to solve the whole problem. The best of them don't introduce new kinds of environmental risks. Most of the risks have to do with local effects and not kind of global risks. Most of them don't introduce new governance issues, although some of them do. But they do address the root cause of the problem, which is removing CO2 out of the atmosphere, and it's the carbon dioxide that's heating up the Earth. On the other hand, the solar radiation management options, like putting dust in the stratosphere, act quickly. We saw that within a year of putting material in the stratosphere, Mount Pinatubo caused the Earth to cool. The best of these are inexpensive, meaning to cool the whole planet, we're talking about billions of dollars a year, which is a lot of money to normal people, but in the overall scheme of the global economy, it's tiny. And they're scalable. You saw that one volcano was able to cool the entire Earth, so it can really scale up to the size of the problems. But they do introduce new kinds of environmental risk. You're toying with complex systems in ways that they've never been toyed with before, and that adds all kinds of risk. And these also introduce new governance issues because they're inherently affecting everybody's climate, and so different people are going to want to weigh in on what's done. And perhaps most importantly, these things don't address the root causes of the problem. They leave the excess carbon dioxide in the atmosphere. So there's all different kind of conceptions, but one idea is just making an industrial facility, and there's different drawings of it, that would essentially take air in and strip the carbon dioxide out of the air. The main problem with this is that there's not that much carbon dioxide in each bit of air, and so to do this I was thinking of a talk on this in Washington a couple of weeks ago, and I calculated that more or less sort of one Capitol building's worth of air per day. You need to strip out the CO2 from that volume of air just to compensate for your daily emissions. So we're each emitting around 120 or 130 pounds of CO2 a day. And so almost anything that you industrial process that has to strip out 120 or 130 pounds of anything that anybody does every day will be not inexpensive. Okay, so then another approach is one that is basically to grow trees, and that tends to be where it's feasible to do it. It tends to be relatively cost effective and tends to have lots of co-benefits because you're preserving biodiversity and you know, there's just you're protecting natural ecosystems. Sometimes you know, there can be sort of less clearly environmentally beneficial aspects of this. For example, some ideas to sort of grow rapidly growing monocultures or, you know, single species that could then be cut down and burned in biomass facilities to generate electric power, maybe carbon stored from that. And so whether that would actually be, you know, how environmentally beneficial co-benefits would come out of that kind of tree farm monoculture is less clear. But at least in some cases, at least just restoring or protecting forests can help store carbon. Oops. Okay, so this is what I was just talking about. So one idea is to take the power plant, I'm losing track of where my button is. Oops, I'm hitting the wrong buttons. Sorry. I'm going to use this then and give up on the, oops. I guess I did enter then. Okay, sorry. Okay, anyway, the idea is to grow biomass, make electricity out of it, separate the CO2 and put the CO2 underground, and so you both replace fossil fuels and restore carbon dioxide. And then there's something that's sort of halfway in between, which is this idea of biochar, where you're taking crop waste and you're sort of halfway burning it and making a charcoal-like substance that will live for a long time in soils and in some places improve soil properties and agricultural productivity, and then you can get some energy out of the combustion also. So again, these kind of things might be effective in certain places, but probably can't scale up too big. Then there are these ideas of weathering rocks that over hundreds of thousands of years, CO2 eventually reacts with rocks. And so you have this, here's a silicate rock plus CO2, and eventually converts to a carbonate rock in silica. And this is sort of the natural process that would remove CO2 over hundreds of thousands of years. And so some people, they can accelerate this up to short amounts of time. Okay, and then there's another rock-based thing. I'm afraid to touch this. I get all kinds of strange. Okay. Okay, ocean fertilization. I'll just leave it to Dan to talk about, because that's what Dan's talk is going to be about. And then, okay, so now I'm going to move on to space-based options. And these are now we're moving on to the solar, moving on to the sunlight reflection methods, which tend to be more controversial, faster acting, more kind of emergency responses, whereas most of the carbon dioxide removal things, if they're good and cost effective, I mean, if they're sort of effective and cost effective and there's no big local environmental problems, you generally like to do those. Whereas these things, you're toying with a planetary system and we've only got one of them, and so most people think that things would need to be pretty dire before you'd want to toy on these kind of scales. So the first idea was just to put something out in space between the Earth and the sun, and this was proposed in 1989. And just the scale of what you'd have to build, I think you'd have to build like a square mile satellite every hour or something like that. It's some, I forget exactly the number, but it's some huge rate like that. I think I see now what I'm bumping into. Okay, so then there's this idea that of making white roofs, which came out of Art Rosenfeld and the Urban Heat Island lab at Lawrence Berkeley. And this idea is basically paint buildings and surfaces white and reflect more sunlight to space. This is probably a useful thing to do for urban heat islands, but there's just not enough built structure to make a difference. And also there's questions of, are you better off having green roofs, planting plants and getting the shade and evaporation, or are you better off making it white? But anyway, again, this could be an important kind of thing for urban centers, but not important globally. Then people suggested putting plastics on deserts and things like that, but that's probably not going to work for environmental reasons. One concept that's achieved some interest is this idea that currently, this is a satellite photo of some ocean area, and these lines here are ship tracks, and so ships leave contrails much in the same way that jet airplanes leave contrails, and it's because of this, largely because of the sulfur and the fuels that ships use. But some people propose that you could spray a fine spray of seawater in the atmosphere, and the little salt particles from the seawater spray would cause contrails and reflect more sunlight to space and cool off the Earth. Anyway. Okay, so then, oops, I keep on hitting that. So then another approach is to do what the volcanoes do and put the tiny particles in the stratosphere. And let me just jump ahead here. So this was just a climate model simulation of a double CO2 conventional, more warming at the poles than at the equator. And that if you reflect a little bit less than 2% of the solar radiation, you more or less restore something like, remove something like 90% of the temperature change. And here's the precipitation change from a 2 times CO2, and then this is 2 times CO2 with reflecting the sunlight. You reduce the precipitation change by something like 70% in the models. And so this is sort of, without going through this figure here, but let me just sort of point to this side here. So this is sort of the temperature change on average from a 2 times CO2. And this black one shows how the temperature change on average on grid point by grid point is reduced by reflecting sunlight. And then here's the change in runoff, which is the precipitation minus evaporation. And so that reduces that by something like 70%. We did some simulations with crop models, which hasn't been published yet, hasn't gotten here, but this is sort of a double CO2 world. Some crops, so we looked at 4 different kinds of crops: rice, wheat, soybeans, and maize, which are corn. And in some places, the climates get better and the crops do better, but there's a bunch of places where staple crops do worse under high CO2 conditions, basically because it gets largely because much of the tropics is just getting too hot for crops to grow well. And then, at least in the models, this adding the aerosols to the stratosphere basically improves crop yields in the model just about everywhere because because basically what you're doing is you're giving the CO2 fertilization to the crops, but you're not overheating them. And so, while all the model simulations suggest that you could reduce most climate change in most places most of the time with these techniques, that the climate models are very simple when compared with reality. And so you have to expect that if you start toying with something as complex as the Earth, that when you start doing something, unanticipated things are going to happen, and those things could potentially be irreversible and unpleasant. Yeah, so just sort of winding up here. Sorry, it took too long. That that reducing this absorbed solar radiation is not the same as reducing greenhouse gases, and it won't deal with things like ocean acidification, and it's more like a painkiller than something that actually or it's an attempt at a painkiller as opposed to something that actually treats the underlying disease. And you know, there's all kinds of things that I didn't bring up, like issues of governance and what does it do to atmospheric chemistry, and what do you do with winners and losers, and you know, what if it generates military conflict and so on. And so I'll just leave it there. And we're doing this, Dan, next, is that right? And so I will pass the baton to Dan Whaley, who will tell you in more detail about ocean fertilization, which I for sure.
Great. Hi, my name is Dan Whaley. Unlike Ken and Jane, who I just have to tell you guys, they won't say it themselves, but you got two of the world's finest scientists here in this domain, and it's a real honor to have them. So just good to know. Myself, I have no qualification to be up here at all. I'm a tech entrepreneur. If you've booked your travel online, you may have used software I wrote at one point. But I got interested in this area, and I've spent about 5 years looking at this particular technique and working with some scientists to bring together the next generation of projects. So I'll tell you a little bit about this specific technique and in the context of Ken's larger framework. Just the reminder slide here, the reason why we're looking at this stuff is that this is from 2 years ago, but even with all the proposals, the climate proposals that people are talking about, even if you said we're going to do it all by the year 2100, we're still way higher than we want to be. And so we need to at least explore whether or not there are options. The CO2 that we put up in the atmosphere can only go 3 places. It can stay up there, or it can go into land, carbon sinks, trees, or it can go into the surface of the ocean and into the deep ocean. And when it penetrates the surface, it creates ocean acidification. So these are slides. These are called train sects. So this is a slice vertically through the middle of the Atlantic, the Pacific, and the Indian Ocean. So this is very high in the northern latitudes. This is the equator, and this is the Southern Ocean. So you're seeing a cut through the depth of the ocean, and what's shown here is the isotope of carbon that's a signature of the combustion of fossil fuels has penetrated into the ocean over time. Here you're going to have higher concentrations of carbon creating ocean acidification, which is a problem for corals. So that CO2 that we're pumping up into the atmosphere is starting to penetrate into the surface of the ocean. It takes a long time. So we've thought about taking actions by doing things like planting trees. Ken talked about that. The UN has an ambitious program they kicked off about 4 or 5 years ago to plant 1 billion trees. Just try to take some of that CO2 out of the atmosphere and create more forests, co-benefit. And so scientists and oceanographers in particular have wondered for a long time whether or not one could do something similar in the ocean. And really they've wondered what the primary control on the productivity in the ocean. So you've got trees that grow on land. You also have plants that grow in the ocean. And most of the plants, the bulk of the mass of plant matter that's in the ocean is very small. It's in the form of cellular organisms called phytoplankton, so small you can't see them. So the things like kelp and seaweed take a very, very minute part of the total plant matter. This stuff takes a tremendous, it represents most of it. And that's a picture of a phytoplankton bloom from space off the coast of Argentina. So they're big and visible when they happen. So this is kind of a conceptual picture of the ocean, but this part is the key part, and here's what we're thinking about right now. So when those phytoplankton grow up here, sunlight feeds those, and they're feeding the bottom of the food chain. So you get zooplankton eat those, fish that eat the zooplankton, and that the phytoplankton die, and the zooplankton excrete what they eat, fecal pellets, and you get a net downward flux called marine snow of particle matter that comes from ultimately those plants that grow. And that forms this process that oceanographers call the biological pump, which is sunlight stimulating the growth of plant matter, which ultimately sinks down to the bottom of the ocean, taking that carbon from CO2 with it. And that process, over 1 billion years, has driven a lot of the world's carbon into deep water. So if you look at the different sizes of the amounts of carbon on the planet, most of the carbon in the planet is in the bottom of the ocean in the form of dissolved bicarbonate and sediment and things like that. Very little, comparatively, is in the atmosphere or in vegetation. And if you include all the sedimentary rock and things that have formed from sedimentary processes over time, that number is even bigger. So that brings us to the question of iron. So what is that control on productivity? You get water on land. Places where you have a lot of water, you have a lot of plant growth. It's very consistent. But in the ocean, obviously, you have water everywhere. So what is the control on the growth of phytoplankton? Well, it turns out that iron is the missing ingredient that drives productivity in many places in the ocean. And the primary supply of iron to the middle of the ocean is from dust storms that blow off of, this one's from Africa, satellite view of that blowing out into the Arctic Ocean, or the Atlantic Ocean. And this is one from China, a big dust storm sweeping off China, blowing out into the Pacific Ocean. So in the middle of the ocean, these are the primary sources of iron. When we go back and we look at the record of the past, which we know from looking at ice cores and from sedimentary cores in the bottom of the ocean, and we look at that sedimentary record of Earth's climate as stored in those sediments, we see that when iron, which is shown by the black line, spikes, that we have big thick bands of sediment, and productivity, which is the orange, and they're almost perfectly matched. And this is in equatorial cores in the Pacific Ocean. So there's a correlation between iron and productivity in some places. And so the question that scientists have had is whether or not iron is the control, whether it's a leading or a lagging factor. So a scientist in particular, John Martin, was the trace metal chemist who discovered the ability, revolutionized the ability to detect and measure the amount of iron in seawater. And he was the guy who had the first really proposed this iron hypothesis, that iron is the thing limiting and really ultimately responsible in large parts of the ocean for iron for the amount of productivity, the amount of plant life, and therefore the amount of CO2 that's being sucked into deep water by the growth of this phytoplankton. And he also proposed the first project to go test this hypothesis by spreading iron back and forth in the ocean. In fact, he actually made a pretty crazy statement, somewhat provocative statement, that the leverage of iron is so phenomenal. For every atom of iron that you throw on the surface of the ocean, you're pulling tens or hundreds of thousands of atoms of carbon dioxide out of solution and into biomass, that a very small amount of iron might have a very large effect on carbon. So if you think that's a crazy idea, you wouldn't be the first one. This cartoon is from 1990. This political cartoonist picked this up. This is a cartoon of John Martin. We'll dump iron in the ocean. Global warming is the greatest manipulation of nature we have ever seen, but we can top that. Not since Star Wars and cold fusion has an idea so gripped scientists. Give me a half a tanker of iron and I'll give you the next ice age. Another jumped up and shouted, the iron will make the algae grow. The algae will soak up the carbon dioxide. We can turn nature on and off like a beer spigot, but we'll be careful. But first the idea would have to pass the most rigorous review. This is the original George Bush here. Cheap, fast, and easy. Looks promising. So that was back in 1990. Since then, scientists have actually gone and tried this. So there have been, since 1990, there have been 14 open ocean experiments where scientists have gone out in boats. They've taken some iron with them, and they have gone back and forth, kind of like a lawnmower, in a boat, and spread some iron out into the surface of the ocean to see what happens. And it has been very successful at growing phytoplankton. So generally, when they introduce iron, they get a response. That response has varied in different places, but they've pretty much always got something to happen, and sometimes a fairly significant response. And modelers have wondered how much carbon. There's a difference, obviously, between growing carbon at the surface of the ocean and having those projects and that activity result in the long-term sequestration of that carbon away from the atmosphere into the deep ocean, into the carbon cycle for long periods of time. So modelers, a range of them have, over the last 10 years or so, have run different kinds of models to say if you were going to do this activity for a long period of time, because you would have to do this for 50, 100, 500 years to counteract and to make a dent in the amount of carbon that we've been putting up there for the last 100 years, which is by way of illustrating just how much carbon we've introduced. They've come up with a range of numbers in terms of how much CO2 we could reduce. And all of those numbers, basically the range is, somewhere between less than 1 billion tons on an annual basis to maybe, several billion tons. Some people come up with numbers that are higher than that. But the takeaway here is that there's a wide range. We really don't know. These are models, and we need to do more experiments to really get better data. How much iron are we talking about? So the amount of iron that you have to introduce to the ocean is extremely small. The number is what's called a nanomolar of iron, where iron is limiting will satisfy that limitation. That's less than about 1/100th of a drop for every 100,000 gallons, so that's about 100,000 gallons of city pool, so it's a fairly small amount. People have proposed doing this by airplane as a way of being more efficient. That airplane used to fight fires, so it's actually dumping a lot of stuff out the back. If you were doing this for iron fertilization, you wouldn't actually be able to see it coming out of the back of the airplane. It's so little, but this is one proposed way. A 200 by 200 kilometer patch would take about 3 days to do in a large plane. Size. The iron that they use is a salt. It's called iron sulfate. It's not iron filings. Some people think it's iron filings. It's a soluble form of iron. This is something that's used in feedstock for agriculture, and you also take it if you're iron deficient, so people eat it. So this is a kind of a time view of what the projects look like. So this is first day. There's a transit leg. You have to get out there, and then you go. This is about 60 days, about two months of time. Spread the iron back and forth here, really, the first couple days. You get small picoplankton that will take that iron up and make it bioavailable to larger phytoplankton like diatoms. Their life cycle is about a month, 3 or 4 weeks, and then they start to die, and they come out of the, as they die, they come out of the water column or they're eaten. And so there's a kind of an export event around that time frame where most of the carbon happens. So there's a number of projects. That's a timeline of the length of projects that have happened before. A lot of those haven't seen the end of the bloom, and so people are proposing more projects to get a better sense of what the character of these things is. So there's the next generation. We've done 14 of these, but people are proposing larger projects now. The previous projects have been maybe 10 kilometers across, 15 kilometers across, which sounds pretty big, but it's really pretty small on the scale of the ocean. Now people are proposing to go for multiple years in a row to the same place to get a sense of what the variability is year to year, and to scale up to, say, 100 by 100 kilometers or 200 by 200 kilometers, pretty big patch of ocean. But just really about the size of what are the medium scale eddies that operate, and you want to kind of center these patches in the middle of eddies to constrain them and so you get a better view of what's happening. They'll want to start separating the iron distribution from the observation of that, using a lot more modeling to really understand all the processes that are happening to design the experiments themselves, and also to look at what the potential impacts, what the effects of doing this might be, in addition to potential benefits. There's a long list of questions. I'm not going to go into those of questions that scientists have about this and that need to be answered before this kind of thing is considered as some sort of a viable option for humans. It's, you know, the reason people keep talking about this is that it's likely one of the largest non-emission source of carbon reductions achievable at a relatively low cost other than planting trees. There's been a lot of work on the regulatory challenges doing this. I think most of those have probably been solved. And there's a consortium of scientists and institutions that have come together to start thinking about the design of those next projects. This is a homepage of this group called the ISIS Consortium that was just launched in February of this year. 12 major oceanographic institutions who want to start asking some of these questions. Obviously, we only have one planet, and I think you'll find that even though we're up here talking about these things and in some cases kind of proposing these things, you'll find a lot of humility in this group in terms of what this means and the relationship between man and nature and who we are. There's a very strong diversity of perspectives on this, and I certainly honor those. But I think we do think it's important to keep asking these questions and to learn more. And that's my spiel.
I like Dan's slides. I think I'll leave those up there. I don't have any slides. So how many people in the audience, how many of you think that if we stopped emitting all carbon dioxide tomorrow, if everybody stopped driving their cars and we turned off all the power plants and you stopped heating your houses and you stopped using energy, how many people think that climate change would stop? That's good. That's good. So what do you think when...
We're always changing. Climate's always changing.
That's true. But what do you think about global warming that's due to the carbon dioxide we emitted? How many people think it would go away if we stopped tomorrow? No? Huh? Anybody got an idea? Well, let me ask it another way. We've already put a lot of carbon dioxide up in the air, right? We've almost doubled the amount that was there before we started emitting a lot of it. How long? It's now, that carbon dioxide that we put up there is going to last about 1,000 years. It's not going to go away for 1,000 years. So even if we did everything that we could to try to stop emitting greenhouse gases, we're stuck now with a climate and with a world where we've changed the climate. We've done it unintentionally, but we've changed it. And that change could get very dangerous. And we know one other thing. We're not going to stop driving our cars tomorrow or stop using electricity. And so we're going to be putting more carbon dioxide in the air. So one thing we know is that we're going to increase the risk, and that the risk that we've already incurred is going to go on for a very long time. And the thing that we don't know is how bad it's going to get. We don't know if we'll just adapt to it, or if we'll figure out how to live with it, or it won't get that bad, or whether things could happen that would be very precipitous and very difficult to deal with. Have any of you seen the maps of San Francisco Bay under a 2-meter? You've seen them? Do you know what they remind me of? These maps show very clearly what the bay would look like if we got 1 meter or 2 meters of sea level rise due to global warming. So there's 2 things that happen when we have global warming. One is that water expands when it gets warmer, so the ocean rises from expansion. And the other is that we melt ice and more water goes into the ocean and it rises. So it's quite possible that we would have 1 meter or 2 meters of sea level rise. The maps of sea level rise.
What's a meter?
Huh?
What's a meter?
1 meter?
39 inches.
3 feet. But the idea is that basically those maps look very similar. The bay could look very similar to look like before we got here, actually quite a bit larger. So these changes would inundate the airports, would flood out a lot of expensive real estate in San Francisco. And so we don't know what's going to happen. So you've heard today from 2 people who have spent a lot of time and energy studying some ideas about what mankind might have to do or might want to think about if things got so bad that we couldn't take it, that the losses of life and the losses of land and the dislocation of people and disruption to our food system and water would get very bad. So they're talking now about thinking about what we would do. We're planning, thinking about how we would deal with this if it happens. Nobody knows what's going to happen. We are worried that things might happen and get very bad, but we don't know exactly what's going to happen. So people that you've heard from today are now coming up with sets of ideas about what we could do. How could we respond? Clearly, we need to mitigate. We need to stop emitting. It's the #1 thing we have to do. And clearly, we have no choice but to adapt to these changes. But if we can't mitigate fast enough, and if climate change happens really fast, what could we possibly do about it? It bears thinking about. But the difference between that and what we've done before is simply the idea that we're going to do it intentionally. We're going to intentionally change the Earth if we do something like this. And that intention, the idea that this would be intentional, is really scary. All right, how many people are scared by the idea of changing the climate of the Earth on purpose? Good. You're rational people.
It sounds like revelation.
Yes, maybe so. But it's a very frightening idea. People who were surveyed in the UK about climate change were asked how they felt about the unintentional but massive changes to our climate that we have already begun to do by emitting. And they said it was regrettable. And then they asked the same people, how do you feel about doing something to reverse this intentionally? And they thought it was excruciatingly terrifying, and they didn't want to do it. So the reason is we don't trust ourselves to know enough to do this. And we will probably never know enough to do this kind of action in a way that we can be sure about what's going to happen. So why do we want to go forward then? Because the bottom line is we still don't know what's going to happen. And we don't know how bad it's going to get. And being ignorant of things that might help us is not a good idea. And so we think that we need to learn more. We need to understand more. And my point to you today is that in trying to learn more, in trying to understand this and do better, we could have a much better idea. We could learn as a people about how to manage this Earth. And we don't actually have a choice anymore about managing the Earth. We're doing it unintentionally. And this is now called the age of the Anthropocene, because the most dominant force on Earth is now us. We make the biggest changes. We have massive changes in the ocean, massive changes to our ecology, massive changes to the life on Earth, and we're causing it. And so we don't have any other place to go. We have to manage it. But we don't have a global society. We don't have a way of managing these kinds of problems. We don't know how to do that. And so what geoengineering represents now in the idea that we could go after trying to understand what geoengineering means, it provides a kind of opportunity for us to learn about how to manage the Earth. Let me give you some examples. Let's say we were going to do what Ken presented today and turn some dials and put a little bit of aerosol up in the air, up in the atmosphere, in the stratosphere, where just a few grams of that sulfate that he might put up in the stratosphere, or his colleagues, and that would offset or erase the temperature effect of tons and tons of CO2. So you could drive your car with impunity, supposedly, for miles and miles with just a couple of grams of sulfate. But it would only turn back the temperature. As Ken showed you today, it doesn't change the acidity in the oceans. It doesn't bring things back to the way they were before. And so we have to ask the question, where do we want to go? What is it, if we're going to do this, what's the goal of doing it? Will bringing the temperature down be the right thing? And if we bring it down, how far should we bring it down? 1 degree? Should we try to match the temperature as it was 100 years ago, or 50 years ago, or 200 years ago, or 1,000 years ago? You can make the argument that mankind has been changing this globe for 1,000 years. Which point in time are you going to pick to try to turn the dial back to? What kind of way can we have a discussion about this? What kind of way can we as a society deliberate what it is we're looking for in the Earth, the only planet that we can inhabit? That's the kind of discussion we have to have. We need to have a discussion about what the strategy is. Is the strategy going to be mitigate as fast as you can, but if it's not fast enough, then we're going to need a tourniquet. Stuart Graham was asked this question, what's the use of this radiation management? And he said, well, it's like you cut your leg and you're on the way to the hospital and you're going to bleed out and die. So you put a tourniquet on, because if you don't put that tourniquet on, you're going to be dead when you get to the hospital. But at the same time, you don't want to keep that tourniquet on or you're going to lose your leg. So the idea is you need to use it for some time until you get things under control. Is that the kind of strategy that we want to pick? And how are we going to have that conversation about strategy? Because we don't even know how to have a conversation about mitigation. We can't get started on it. But maybe because geoengineering is so completely outrageous in its idea, it'll actually give us a little space to have those kind of conversations. So my point really, and I'll just be really brief and we can get to a Q&A, which I'm sure you'd like to do, is that this geoengineering concept is where the idea of hubris absolutely collides with the need to be responsible for our planet. We have two very conflicting ideas here. We need to be responsible. We have to manage. We cannot any longer be unintentional about it, because unintentionality is leading us down the road to perdition. And we must have an intentional management. But that intentional management is really a problem because we actually don't know how to do it. So how are we going to deal with this? And this is the challenge that geoengineering presents to us, to every person in this room and every person on this planet. And this is the thing we have to solve. This is what our children and their children have to face. And that's why this presentation to you today was so incredibly important for you to know what this is, because this is the world we're going to face, and this is the world your children are going to face. Thank you. Anybody got a question? Yeah.
I was curious to hear your thoughts on the potential of working in barren ecosystems. I feel like the part that scares me about working atmospherically and oceanically is that these relatively, these evolved ecosystems that have evolved without our direct interference, and certainly implementing some intervention is gonna have unknown consequences. But Gaviotas in Colombia, where it's thousands of square miles of barren landscape, and the former head of the United Nations Environment Program has figured out how to get a forest to grow. That's a great idea. I've never been to the Sahara, but the Sahara Desert, hundreds of thousands of square miles of what I perceive to be barren landscape. Are there people looking at these sorts of places for carbon sequestration?
So let me just start off by saying that what you perceive as a barren landscape, not everybody else perceives as a barren landscape. And I mean, this has come up in Southern California where people wanted to put solar farms in the Mojave Desert, and there's turtles that live there and things like that. And so, anytime you try to modify any landscape at a large scale, you run into issues. The other thing is, typically you get lots of carbon storage in ecosystems where you have lots of water. And the ecosystems that you're describing are typically the reason they're barren is because there's not much water available there. And so, so it's just not that easy to get forests to grow in the middle of the desert.
There is some work to look at Northern Africa, for example, and to reforest. Northern Africa used to be forested. The Romans really deforested it to build ships and things. So there have been people talking about reforestation. All of these issues have unintended consequences of any of these actions, and that's really the nugget of the problem with the kinds of changes people are contemplating, is you don't know what else is going to happen when you do it. Okay, right there.
Two short questions. One, about 20 years ago, I read a little piece in the newspaper that said that grass, like prairie grass or savanna grass, absorbs a lot more carbon dioxide than the same acreage of trees would. And the second comment and question is, you mentioned the leverage that iron has, and then you said that it would take 500 years for an iron dumping program to absorb the carbon dioxide that is excessive. But the big excess has only happened in the last, say, 150 years. So how come with all that leverage you'd need 500 years to absorb 150 years of carbon dioxide?
Right. I'll take the second question. The problem is that the ocean is driving about half the carbon cycle annually on the planet right now. So the instantaneous annual turnover flux of CO2 oxygen, about half of that happens land-based photosynthesis plants and so forth, and about half of that happens in the ocean, primarily through biology in the ocean. And it's already driving, that biological bump in the ocean is already driving, the number is like 60 billion tons of carbon dioxide into deep water every year. But that system has a natural range of variability. In past climate cycles, we've seen much greater flux, but you can't just turn it, from 0 to 100. There's only a limited amount that you would be able to do, even under the most optimum conditions. We're continuing to put a tremendous amount of CO2 up in the atmosphere now. We've put a lot in the past. So the range of times, from 50 to 500 years, if this kind of a thing is even possible, is really just kind of partly an indication of the range of uncertainty around the effectiveness of the technique, and partly an indication of the scale of the problem.
To come to your first question, in general, forest ecosystems store more carbon than grassland ecosystems, but there are certain places where there are very deep-rooted prairie grasses. I think in Argentina they exist, and a few other places where the roots are very deep and they bring a lot of carbon deep into soils. And so there's a lot of heterogeneity and spatial difference. In general, forests store more than grasslands, but some grasslands are very effective at storing carbon.
Yep.
Mhm.
With iron fertilization, how would it affect the marine life? Like, what negative impacts could it have on the food chain and
Right.
the animals down there?
Well, great question. So it's a research, first of all, just to give you the caveat, it's a research question. Understanding that is important and important before anybody would move forward. Phytoplankton are growing vigorously in the ocean. It's what fish eat. So, and we know that there are periods of time where we've had much greater growth of phytoplankton globally. That's resulted in extra carbon going to deep water. And we've had, in the last million years, 6 of those periods, actually. So we know that that kind of cycle happens before, that the biodiversity that we see on one side of that in the ocean is about the same as we see on the other side of that. We know that the ocean is adapted to blooms. So, you know, when a dust storm blows out into the middle of the ocean, you get a big bloom, much larger than anything scientists are thinking about creating in the next 10 years in any of these projects, by an order of 100 or so. So I think the combination, you know, there are kinds of phytoplankton blooms. We see blooms in coastal environments here where you get agricultural runoff, you get big blooms near shore in shallow water environments. That biological material will fall to the ocean floor and decompose and suck up oxygen. You'll get an anoxic environment, an HAB, harmful algal bloom, they'll call them. You get a big fish kill. Other kinds of phytoplankton sometimes can be neurotoxic. They think that the movie The Birds, the Alfred Hitchcock movie, was about a neurotoxic bloom potentially of pseudonychia that produced domoic acid. The birds ate fish that ate phytoplankton and they went crazy, and Alfred Hitchcock made a movie about it. So there are questions. Other people would say, actually, people have said maybe it's their urea in the runoff from our agricultural or our urban environments that's the trigger for that domoic acid, or there may be other environmental signals. These are questions I think we need much better answers than the ones that we have now.
Can I just jump in there? You know, Dan showed these pictures of these giant dust storms and the Gobi dust lands on the North Pacific and Saharan dust lands on the Atlantic. And, you know, every proposed experiment is so tiny compared to these naturally occurring dust storms, but it sort of was getting to Jane's issue of governance, that it raises these kind of slippery slope issues that sort of everybody who's sort of looked at it recognizes that the experiments themselves are benign, and then the concern is how long does it stay benign, what scale could you bring it up to without it having significant adverse impact, and that's what there's a lot of discussion and people disagree.
Are there any discussions on what topics are coming up in the last month about what we might want to do for radiation in the seas? Are people talking about dropping boron or other salts or metals to bind radioactive isotopes?
In the ocean.
From Fukushima.
From Fukushima. No, I haven't heard anything but that. It's a small, relatively small amount in the larger, you know, when it's mixed into the larger environment of the ocean. I mean, I think one of the issues about Fukushima that's you know just very difficult, I think, for people to absorb is that when you actually count the harm, when you actually count the numbers of people that were hurt, and you count the actual harm from what happened, which was a rather massive failure of nuclear power plants under really extreme conditions of the largest earthquake and an enormous tsunami coupled on top of each other. And furthermore, that the failures were mostly due to fairly low-tech issues like putting the generators in the basement and where they stored the the spent fuel, not in the basic safety case. And in fact, the nuclear power plants came through the earthquake itself remarkably unscathed. So it was really the tsunami that got them. And then if you actually add up the numbers of how many people were hurt, these are actually very small numbers compared to how many people are killed by using coal or other forms of energy. So even windmill blades flying off, I think hurt more people than have been hurt by nuclear power plants. But the effect of that, the effect on people and how you feel about nuclear power is enormous. And that's really an important factor to remember, because we really don't hear as much about how many people are killed and how much environment is disrupted by coal-fired electricity, for example.
Well, it's truly only a beginning now of 3 or 9 months where they're going to be working and addressing Fukushima, then we have not begun to see the long-term effects with cesium with the half-life of 6,000 years, etc., plutonium 250,000 year half-life.
There's a lot to learn.
The cumulative effects on our bodies is quite something, especially when interactive with coal and smoke and mercury on particulates. Certainly workers in coal mines who also had exposure from Chernobyl had an increased interactive risk. When you take toxic plus radioisotope, you double your. So, and I often am scared when people say, oh, nuke's bad, let's do coal, or coal's bad, let's do nuke. Let's try to turn our lights out a little bit and bicycle to work and carpool and walk and reduce all these uses, because I wish we would, as a people, stop fighting for one or the other and try to just green out.
Yeah, well, we can talk more about that. Just coming off chairing a study for the state of California on California's energy future in 2050, and let me tell you, you're going to need it all. So it's not just a matter, you have to have the efficiency, you have to have the change in behavior, but you still need the sources of energy to maintain the lifestyle. And I think basically it's a really difficult problem to reduce. So let me get somebody all the way in the back.
A couple of questions. One, about the effects that genetically modified organisms are having on the planet. And two, what would be used as a bonding agent to spray this ferrous sulfate into the air, and what would the effects of that be on pretty much every living organism on the planet?
I don't know that we have any expertise in GMOs here on the panel, do we? So we'll
There are plenty of studies that have come up that are proven that it's very extremely dangerous to all of us, to every single living organism on this planet.
I mean, we're not experts in GMO up here, but a lot of the governance issues are similar to some of the issues that are raised by some of the things that we're raising up, because presume, a GMO that's introduced in one place.
Basically what I'm saying is that stopping GMO would really be a really good solution. It would help a lot. It would really, really help a lot with a lot of the issues that we're having. There have been studies that have linked, when the honeybee population started dropping off drastically, there were some independent studies that were done that linked them eating genetically modified crops.
We're just not experts.
Yeah, so
So
if you
we-
want to answer the iron sulfate.
The iron sulfate question, you said spraying iron sulfate, ferrous sulfate in the air. I think you two different techniques. The ferrous sulfate is the compound that they're thinking about for ocean fertilization. What's the impact of that? Well, it dissolves into two components. One is iron and the other is sulfate. Sulfate is the fourth most abundant iron in seawater naturally, so there's a more sulfate in seawater than you can shake a stick at. It's kind of like saying, I'm going to spray a bunch of NaCl in the ocean. Well, it's salt. So sulfate is common. Iron is in very short supply and readily absorbed by organisms that need it as part of their natural cycle. So I don't think ferrous sulfate is a problem. I think that probably the much larger problems to think about are what are the impacts of doing this in terms of growing lots of phytoplankton, and should we be doing that, and the scientists want to try to understand the answers to those questions.
And is it effective? So, the questions that will come about when we start thinking about these ideas is, one, do they make any difference? And what are their harmful effects? What are the unintended consequences? And, do the benefits outweigh the risks? these are the kinds of questions people have to ask, and they're not easy to answer. And furthermore, I would say we're never going to be completely able to answer them theoretically. And that's really a problem. Yeah, let's get you here.
So let's say that UN plan went through, that they actually planted 1 billion trees. How much would that actually do?
Each, I can answer.
Yeah.
Right? So each,
Redwoods.
Yeah, well, redwoods I don't know, but a tree that's like a foot across has about a ton of carbon in it. So I mean, your order of magnitude then would be 1 billion tons of carbon, which is 10% of 1 year's
In 30
global
years.
emission. Yeah, right. So as it grew over 30 years, you'd get 10% of 1 year's CO2 emissions. So it's something, but it's I think this thing about planting trees, native trees, and I think this idea of native trees too. I think this issue of co-benefits for these things is really central, and that sometimes we forget that one of the main reasons for preventing climate change is to preserve natural ecosystems, and so sometimes we flip things around where we forget what the goals are, and so people start destroying natural ecosystems because it will slow climate change, and so in the case where you're restoring an ecosystem, that's the prime benefit, and then this carbon storage is secondary. In the same way that I think if you cut down rainforest, the primary insult is to the rainforest, and the carbon emissions is really secondary.
Question back here?
Yeah, I have a question regarding.
We can't hear you too well, so.
Yeah, sorry. The military use of some of these technologies for their own purposes. The Air Force has a website, owning the weather by 2020 or 2050, and it's like
2025.
2025. Okay, that's the number. It's a light that I skipped over it, and then I said. No, there must be something to this. It keeps popping up. And the idea of using this electromagnetic energy, which in nature's term could heal everything and everyone on this planet if we knew more about the beneficial effects of the Schumann's Schumann resonances. But they take it out of context and do these extremes where they use energy to lift the ionosphere so that they can better communicate with their buddies on the other side. I mean, if their buddies were planting trees, okay, that'd be cool, but they aren't. They're doing the opposite. So, as scientists, please don't feel helpless.
Well, I think I'd rather than address directly the issue that you bring up, what I'd like to do is talk about the point that you can go to the web or go someplace and get some information about something and think that there's a conspiracy to do something to the planet. And the real issue is that we as a society need to find out about this, but we need to find out about it in the most absolutely transparent way so that people can understand what is being learned and put it in the right context for what they face and what their children and grandchildren are going to face. And this has come up before in other kinds of science. We brought up GMOs, other types of high risk, recombinant DNA type research that is also risky, and people need to have a very good and clear understanding of what research is being done and why, what the results are and what the results aren't. This is the challenge of the research community right now, and something that the research community has been focusing on very closely. We had a meeting last spring at SLMR. There was recently a meeting in the UK just a couple of weeks ago, looking at how is it that we make sure that any knowledge that we gain about these technologies and how they might be used is available, accessible, and understandable to people in society.
I think also that one of the things that you get out of studying climate system is that the whole world is connected, and it's impossible to change the climate in one place without affecting other places. And so it's kind of hard to use these techniques as a weapon. I think the bigger military concern is that the use of these things could potentially incite military conflict, or if it had positive outcomes, could reduce tensions that lead to military. But I don't think the potential for weaponization is really very large.
It is.
It is.
No, I think the technology, but put it this way, okay, I mean, the military has a lot of direct ways to inflict harm, and that this is a pretty roundabout and indirect way.
And difficult to control. So we have one more question. Let's go in the back.
You talked about, Ken, in your presentation, you talked about one of the things about carbon removal, obviously, was the iron filings and the phytoplankton. I'm presuming it's one of them. That there's no new environmental risks, which we're questioning here, but also that there's no new governance.
I said with most of them. I did actually, the one that does have new governance issues is citing Belarus.
I was going to bring up the governance issues thing and talk. Are people talking about that? Whether or not you do this in the open ocean, you're going to have tremendous governance issues of deciding when to do that, how to do that, how do you manage this common resource. And if countries do it within their territorial waters or their exclusive economic zones, you're also going to have tremendous governance issues because this is not, that you're going to have environmental effects not limited to those. So are people talking about those governance issues and how you actually manage this among the nations of the world?
Yeah, and I'm sure Dan will jump in on this too, but I guess what I was talking about was most of the ones that are land-based, where somebody's owning the land. It's more about the local environmental impacts and doesn't introduce governance issues. But anytime you have an experiment, whether it's in the ocean or the atmosphere, where you're involving global commons and things are being transported across international boundaries, it raises all kinds of governance issues. And there is something called the London Convention, London Protocol, which governs dumping things in the ocean. That's been addressing this issue with respect to scientific experiments. But really, if it ever got into sort of commercial scale things, that would need to be developed.
Yeah, there's the questions on the iron fertilization in particular are ocean questions. There's a place for those. People are already doing this. There's an umbrella organization that handles stuff that's outside of the EEZ that happens in the deep ocean, the London Convention. The stuff inside the EEZ is covered by sovereign environment, the sovereign environmental authority wherever it is happening. And it's not necessarily iron fertilization, but certainly fertilization for aquaculture happens extensely already in EEZs, and so there's a lot of questions about how extensive that should be, and those are important. The trade-off between growing fish and harvesting them out of the ocean, all kinds of questions like that.
So do you want to, it's up to you. Well, you have more questions.
One more question.
Let's take one last question, and I'll bring the mic over.
Okay.
Good evening. Thank you for being here. I just want to ask, how about the governance in relationship to the World Trade Organization that's got its finger in everything?
Yes. What?
I don't see any connection myself, but I don't.
Yeah, well,
Not with this topic.
Yeah, well, the only way it's come up with is this question. I mean, it's not really this topic, but on carbon emissions. If we had, say, a carbon tax or something like that, could we then put a carbon tax on imports there? That's where the WTO would come in.
I'm thinking in terms of what happens with the iron fertilization and the food chain, and Slady asked about what would happen in the oceans if we changed dramatically the population of fish up and down, and how does the World Trade Organization see a place they can take on and take over and get involved? Something that could happen with the way.
I don't think we have any way to comment on that, but I just want to make one kind of general comment, which is that basically some of the questions that you guys are answering are about very specific and targeted interventions, like a country using this for war or WTO getting involved in some way. Don't forget that the most insidious and the most difficult problem is the thing that happens every day by millions of billions of people who are living their lives and driving their cars and heating their houses and using electricity, and that happens at a scale which is absolutely massive and very difficult to stop. So if you get yourself really distracted on, these the smaller kind of they're juicier stories, but they're not as important as the thing which is inevitably and inexorably changing this planet every single day, every single hour. So don't lose track.
All of us emitted 130 pounds of CO2 today.
And I'm going to go home by BART, but I will drive my car from the BART station home.
I want to thank the speakers and thank everyone for coming.
I think there's what a joke.
That was 7:30 questions and answers. Did anybody ask a question that was pertinent to what we have? Well, I know, but I thought it until 7:30. I said no more questions. I like the way she said there will be one more question after starting question and answer, like it was going to go on to 7:30.
Climate change.
Please.
Right, but this is actually, I was sitting and trying to find my life quick, so it was actually very
Tell Will that.
If I may, I got a question. Growing up in the 60s and 70s, my dad and I used to look at clouds all the time. We would see the cumulus clouds, you see cirrus clouds. Now, everybody's talking about it. You see these long striations throughout the sky. You see planes, wait, hold on a second. You see planes from horizon to horizon, and these things don't dissipate. They expand, they contract, and they make the entire sky milky. And I believe you're in the film, What in the World Are They Spraying? You're at the symposium in San Diego. And Dane Whittington, who's an expert in solar energy, who owns 2,000 acres in Shasta, his energy is depleted 60%, solar energy 60%. They do all these tests. They're peer-reviewed reports too, I believe. You're scientists. And they show you that strontium, barium, and magnesium and aluminum have skyrocketed throughout Shasta County. And they notice it's happening in generally the NATO countries. So what is that? If you guys aren't doing this geoengineering, what the hell is it then?
Yeah, well, I don't know. I mean, first of all, I don't know if it's real or not, but if it weren't, of course, I don't believe it's real. I think it's just normal jet contrast, but I don't really have all the information. But I'm pretty sure it's not climate, because just hear me, that I don't think the Bush administration and Dick Cheney cared enough about climate to have a secret program to try to address the climate issue.
Do you think President Obama cared?
No, I don't think, not really.
I can't stand that.
That's what I'm saying.
anything.
But I'm saying, what I'm saying is, I think that, you know, and I've talked to people, you know, who have military backgrounds saying, oh, well, do you think it's maybe part of some radar interference thing, and you know that, and they said, well, no, there were experiments on that, like with World War II, of putting particles out to interfere with radar, but that experiments, nobody's doing that anymore.
But do you know Rosalia Peterson, who was actually working for the FDA, and she was actually hired through the government to go out there and analyze the soil, and she found out through the study of the soil to see why all the crops were depleting and the trees were depleting. She noticed all these striations in the sky, and she went to the FAA and she asked the FAA to give all the reports on all the interflight, and she proves in her video and presentations around the world that the FAA released at NASA that these weren't standard flights from just commercial airlines. These were all the military. You can see it, you can Google it, I'm sure you've heard of her name. And you didn't answer my question, though, about Jane Whittington, when they find out that 375,000 particles per billion are in the soil and in the snow and in the water. How do you account for that? And they're noticing the same thing. He's an expert who worked for Bechtel for years. It is going on right now. It's been going on for at least 18 years. The geoengineering. I know you know it is.
No, wait. Well, first of all, why do you say things that you don't know to be true?
Because I do. You know, I ran for Congress last term, and did you ever see the film When the World May Spring? Okay, well, they go to Congress with it. They go to Congress with it. They present it to Dianne Feinstein and everybody else. Here's what you get. You haven't seen this film? It's wonderful. It came out last year. As scientists, you really need to see it, because in that film they also ask, what detrimental effects is it going to have on human population or the animal life? And they said, your scientists you're with said it could be terrible. We don't know.
The question is, what would be the effects of these materials on human health if they came down into the stratosphere, in particular small particles and aluminum?
So the collaborators of mine working on the aerosol scheme are actually folks from Carnegie Mellon who focused on human health impacts. And while we haven't published it, that was the very first thing we did, was do the order of magnitude calculation in level pencil and paper, but with an expert on human health impacts about whether there could be an issue. And for aluminum or other particles, there are a lot of toxicological things that need to get looked at seriously. But if you're just thinking about the sheer number of particles and the human health impact of small particles, the answer is, well, we haven't published it. That was the first thing we looked at with some of the leading experts who do epidemiological research on human health impacts, and it's not even close to being an issue.
So 10 megatons of aluminum dumped into the atmosphere would have no human health impact.
So let me be more careful here. We're to separate out the toxicological. So the alumina, we've only begun to research and published nothing.
When are you going to know? And why are these lines? Why are these lines throughout the sky now? Why is my dad at age 87 saying, who was in intelligence in the Army for years, saying this isn't natural, it's geoengineering?
Well,
Contrails. These aren't contrails. These are going from horizon to the horizon. Contrails, hold on a second. You guys are scientists. Hold on a second. Contrails, it has to be 47 degrees below zero. It has to be the perfect atmosphere for it. We're talking about in Shasta County, it was 102 degrees that day.
But why do you think it's climate change? Why do you think they care enough about climate change?
I'm a pilot.
Well, that's fine.
So I know what the temperature is at 30,000 feet, and it's not 100.
So why are you seeing them? They used to go 25 lengths of the plane. Now we're seeing them from horizon to horizon. And why are they finding?
Why do you think it's climate change? Why do you think
why are they finding barium? Why are they finding strontium? Why are they finding aluminum? Why are they finding magnesium?
Answer one of my questions. Why do you think that they care enough about climate change to have a secret program to address the climate
tell
issue?
me. You guys are the scientists.
I don't think.
My question to you is, why was Rosalia Peterson, who travels the world, who has a scientific background, why is she showing NASA in the FAA report showing these aren't natural flights, these aren't normal flights? You're a pilot. Why is that?
Answer me one question.
Contingencies. They want contingencies. Okay. What do we do if the earth races hot?
Okay, but first of all, if you want to, if you want a contingency plan, then you'd be looking at putting particles in the stratosphere for climate. And so just having these planes flying around the upper troposphere, that's not where you do it. And so, first of all, my guess is they're contrails. I haven't studied it, but I can tell you that Dick Cheney does not care enough about
I
climate
know
change.
that. I'm not talking about
So
Dick
then why do
Cheney.
you think that there's a secret program to address the climate
Tell
issue?
me this.
No, you tell me. Answer my question.
2025, stated
If you're not
goal.
going to answer my
Well, I
question,
don't trust you. I'll
Okay,
tell you
well
the
then I'm
truth.
not going to
But
talk.
tell me this. When Dane Whittington presents this to you, why do you not see his movie at least? And why do you run off?
Because if somebody doesn't trust me, I don't talk to them.
It's happening. I mean, they're already doing it. We know it. But if you're a pilot, you know what's going on.
It's the stated
If
goal
I'm
by
a, well, first of all,
2025.
there's lots of pilots that don't necessarily know everything that's going on.
Well, that's for sure. But you're telling me that's a normal contrail we're seeing throughout the skies in grids?
See, yeah.
For Horizon,
Jet
Horizon
planes make
expanded.
Expanded? They
Yeah,
didn't
they
do?
They did not.
But did they make them before 1998? Have you seen any picture pre-98
No,
with
you
the
don't.
line going from horizon to horizon?
You're telling me that
old.
contrails didn't exist?
25 places to plane generate.
Persistent contrails.
Expanded to wispy clouds throughout the
A
day.
normal
look at photos
contrail
pre-98?
will last for a minute. These expand into clouds.
So
Go to the
let me
airport.
ask you guys a question.
Yeah.
Okay, because you guys are saying a bunch of stuff. I've generally looked at chemtrails. I'm not part of the government conspiracy that's doing them, so I don't know. So I'm asking you guys.
Sure.
Okay.
It's private also.
So let me just ask you some questions. Okay?
Sure.
Yeah.
Military and commercial, or just military?
Evergreen. You used an evergreen plane in your slide projection. Evergreen. They're a company using them.
One proposed way.
I met a pilot.
Let me just ask you a question.
Okay, please do.
So, commercial and military, or just military?
No, I'd have to say military.
Okay, so therefore the contrails coming off of commercial planes would be different than the ones coming off of military.
No. Now hold on, I can get you on this one. How many times have I looked in the sky and noticed a commercial airline? I live right near Oakland, San Francisco area.
Yeah.
I know where they're flying their routes every day. You'll see them coming, okay? 35,000 feet, okay? I'm in Martinez, so I'm east of this.
Sometimes
There's
they have
no
contrails,
hold on.
sometimes they don't.
There's no contrail in the same height, you can tell, same size plane. I've had binoculars on, everything else. That plane has a gigantic contrail, you call it.
Absolutely.
Why?
Atmospheric conditions change. What are that as a pilot?
Same time, same line.
Same level.
Oh, okay.
Commercial
You're saying there's two
Yeah,
two
scientists.
planes. I haven't observed that phenomenon, so I don't know.
Okay, well, here's the evidence.
Hello, the library's closing now, so please make your way to the upper level. Thank you.
So yeah, look at pictures pre-98, look at pre-98 photos.
Pre-98, okay.
And does that have to be a starting point?
Contrails in this phase is the result of the contrail spreading out. Even if it's not sinister and it's only water vapor, isn't it not geoengineering?
Yeah, well, they don't. It's all controlled.
Yeah, I mean, everything that we do is geoengineering. Certainly contrails reflect stuff into
Okay, everyone,
the...
please. Time to
Well,
go.
hey, thank you, though.
Alright, so you guys like the...
Hey, would you watch the film? What in the world are they spraying at least? My goodness.